All right, so today we're going to start talking about domain and range and functions. So a function is a relation between x and y such that x does not repeat. Okay, and then we know that the domain is all the x values. You might have heard of Döhler-Ribet. We're going to use that some. And then the range is all the y values. So before we start, let's go ahead and just show that x equals y squared is not a function. So if x equals y squared is not a function, let's think about, I'll just give you a x value that shows that. So x value of 4. So if you plug in a 4 right here, what is a possible y value that would get you that? Well, we know 2 squared is 4, but what other y value would get you that? So you could also have had -2, and that still results in the x value of 4. So this is showing why it's not a function, because you have the x value of 4 gets you a y value of 2, and that same x value of 4 gets you a y value of -2. This is showing that x is repeating, which is not okay. And you could have done that for, you might have thought about 9, which would have been 3, and -3 still would have been 9. So that's another example of why that's not a function. If you're thinking that this seems like a really familiar function, it should seem like a familiar function because we know that y equals x squared is the parabola, and this is just that exact opposite or inverse. So that's why when I graph it, it's going to look just like x equals y, or y equals x squared. It's just going to be on its side. So 0, 0, 1, 1, and 1, -1. 1, 2, 3, 4, 2, and 4, -2. 5, 6, 7, 8, 9, 1, 2, 3, and -3. Okay, so it looks just like a parabola that's been turned on its side. So that would be the y equals x squared that you're all familiar with. But this is x equals y squared, so we turned it on its side. Okay, and this is a great example to show you the vertical line test, because the vertical line test says any vertical line will touch a function at most once. And the reason why I say at most once is because it's okay if it doesn't touch it at all, but if it does touch it, it's not allowed to touch it more than one time. So the example on the graph x equals y squared is so, of course, oops. Let me see. Oh, this vertical line, that would be okay, right? Because it's not touching it at all. But if I move this vertical line over here, then that's showing you it's going to fail because it touches the function here and here. And so this is why it's going to fail the vertical line test. Okay? All right, so let's do some more vertical line tests. So in example 1, I want you to first say if it's a function, so yes or no, and then state the domain and the range as well. So I want you to look at example 1a and decide if you think that's a function or not. All right, so if I put in a vertical line, let's say I put it in right here, then that touches it only one time. So that's okay. Anywhere you put that vertical line, it's going to touch it only one time. And so yes, this is a function. I'm just going to set this vertical line to the side. So yes, a function. Okay, so let's talk about what the domain and range is. And really, this should have had some arrows right here and here, just because that's what's going to tell us that it goes on forever. So when I do the domain, domain is dolar left to right. So on the left-hand side, this arrow tells me I'm going to go forever left. And then as I move to the right, I'm still existing everywhere to the right. And so that's everywhere to the right. So I write that as negative infinity to infinity. Okay, and then my range, bottom to top. So my bottom, there's nothing down here at the bottom. As I move to the top, I start to exist right here. So let's call that point A. And I really should have, I was meant to touch that. So at A, I start to exist at the bottom, and then I go up forever. So since I do get to touch A, and then I go up forever to infinity. All right, let's do B. So decide for yourself if you think B is a function. So I'll bring out my vertical line again. So over here, it doesn't touch it at all, which that's okay. But when it does start to touch it, if you notice, it touches it in two places. It touches it here and here, which means it does fail the vertical line test. So this is not a function. Because it touches it here and here. All right, we can still figure out what the domain and range is though. So my domain, there's nothing over here on the left, and then as I move, I start to exist right here. So let's call that point B. So that's B to infinity. Again, these arrows should have been there. All right, in my range, bottom. So even though you don't see anything at the bottom, this arrow is slightly headed down. Slightly headed down. If you do that forever, you're going to go forever down, and you're going to go forever up. So that is forever down, negative infinity, and forever up is positive infinity. All right, and question C. So here's my vertical line. That only touches one time right here, so that seems good. If I put that vertical line somewhere else, that's still okay. It only touches one time here. Now the questionable place is right here. But if you notice, that dotted line is there as well. What that dotted line tells us is that actually neither one of those graphs is going to touch it, not up here nor down here. So even though it seems like it might run into trouble, that dotted line, it's actually called an asymptote. If you remember that word, that's great. But what that means is it's never going to touch it. So the only questionable place, by definition, the asymptote says it's actually never going to touch it in either place. So this is another function, yes, a function. And so my domain, let's bring out this line again really quickly. So remember, this line, the asymptote, says I'm never going to touch it. So that actually helps the domain because that reminds you that it's going to be forever left, but then you're never going to touch that line, and that line is at -1. You're going to skip over -1, and then you're going to go on forever. So I'm going to erase some of this. So -1 is the only skipping point. So I'm going to go negative infinity to -1. I don't want to touch it, so I'm using parentheses, and then -1 to positive infinity. And then my range, you could do very similarly. Your range is going to be everywhere except this. Now it's a horizontal line. It's a horizontal asymptote. Same idea though. Bottom, it exists everywhere here, but as I move to the top, I got to skip over, and it looks like that y value is 3. Skip over 3 and then go forever up. So negative infinity to 3, and then 3 to positive infinity. So if you want to think about this in numbers, sometimes it's helpful. This is like saying go negative infinity to 2.99999. Since you can't list out all the 9s, that's what this is really showing, is that get as close to 3 as possible without actually touching it. skip over that 3, and then start again at 3.00000, so start as close as you can to 3 without touching it, and then go on forever. Okay? All right. So let's go on. So find the domain of square root x minus 1. So this is a square root, and the rule for square roots is that square roots can't be 0. Graphically, some people think that this is easier if you think about it graphically. This is the parent function, y equals square root of x. So if I have square root of x minus 1, it's going to be that same function, but translated to the right one. So I'm just going to do this in red. So if I go to the right one, it looks like this. And so the domain of that red function right here is going to be from 1 and then onward forever, 1 to infinity. Now, why is it that way? Well, again, let's think about the parent function. The parent function is the one in black. So this black one that I did, I said start at the origin and go this way. Why did you have to start at the origin? Why couldn't you have been over here at the negative numbers? Well, it's because you can't take the square root of a negative number. And so that's going to be the algebraic rule that we're going to have to remember here, is that for square roots, the algebra rule is that the radicand, which is the thing under the radical, the radicand you're going to set to be greater than or equal to 0. So x minus 1 is greater than or equal to 0. Add 1, and you get to here. Okay? All right, on example 3, x cubed plus 2x squared minus 1. This is what's called a polynomial. A polynomial is just a degree term, x to some degree. And polynomials have all real number for their domain. All right, so let's do some more just function rules. So in example 4, this is just practicing some basic algebra. We want to find the value of f when x is 2. So this is just saying plug in an x of 2. So evaluate the function at 2. So I'm going to do 2 squared minus 3 times 2 plus 5. So that's 4 minus 6 plus 5. Negative 2 plus 5 is 3. So you could say f evaluated at 2 is equal to 3. Okay, question B, f of a. So this is just saying for whatever reason they want to use the letter a instead of x. So we're just going to say, well, that's a squared minus 3a plus 5. And that's all that is. The last one, f of x minus 2. So let me just rewrite f of x really quickly. Is x squared minus 3x. I'm just rewriting the problem. Now, what this is asking us to do is instead of using an x, it wants us to use x minus 2. So instead of x, I'm going to use x minus 2. I'm going to have to square that. Minus 3. Instead of x, I have x minus 2 and then plus 5. So this tells us we have to take x minus 2 and square it. So that's x minus 2 times x minus 2. And then I'll just rewrite the rest of this. Minus 3x minus 2 in parentheses plus 5. All right, so FOIL or whatever you call that. X squared minus 2x plus 4, distribute minus 3x plus 6, make sure you distribute correctly, and then plus 5. So if you combine your like terms, so I have a final answer of x squared minus 7x, 10, 15, plus 15. Okay, and that's it for f of x minus 2. All right, and then we're just going to do some more practice of domain. We're going to practice this again tomorrow. But again, 5a, this is a polynomial. Polynomials are defined everywhere. B, this is another square root, and square roots have to have a radicand greater than or equal to 0. So subtract -3, or I guess I should say subtract +3 and you get -3. So from -3 to infinity. C. Now, C is one we haven't really done yet. If you look at 2x squared, that's just a polynomial. There's no restriction there. And then 5 minus x, that's also no restriction. So far I have all real numbers. But then I remember, well, when you have something in the denominator, denominators aren't allowed to equal 0. So the only restriction I'm going to give you is that 5 minus x can't be 0. So if you solve for x, you're saying 5 cannot be x. So choose anything else but 5. So on a number line, how you represent that is, here's the 5. You're saying you can be after 5 or you can be before 5. Just don't be 5. So that's -infinity, and then eventually you get to 5 and you want to skip over 5 and then go on. Okay. So in question D, we have 7 minus x and then square root 2x minus 1. So let's do it kind of in the same way. We look at that top and we say, well, there's no restriction there. And then if I look at the bottom, I say, well, that's a square root. And square roots have to be greater than or equal to 0. But not only is that a square root, but it's a square root that's in the denominator. And when it's a denominator, it can't be 0. So if you put together these two things, you're saying it has to be greater than or equal to 0, but then you say don't be 0. So basically what we're saying is because it's a square root that's in the denominator, it has to be greater than 0. We have to take away the or equal to because of the fact that it's in a denominator. So 2x minus 1 must be greater than 0. Add 1 and divide by 2. So that's half to infinity. Okay, on the last one, so square root of x is on top, and then just 2x minus 4 is on bottom. So first we say square root of x. Well, that's a square root, and square roots have to be greater than or equal to 0. So let's go ahead and do that. X has to be greater than or equal to 0, and so that's a restriction. So far we've only got one restriction. Let's keep going. Now 2x minus 4, well, that's just a linear function, so that gives me no restriction. But not only is it a linear function, but it's a linear function that's in the denominator. So now we got to say, but don't be 0. Just because it's in the denominator. So now I got to say 2x minus 4 is not allowed to be 0. So if you add 4 and divide by 2. So now let's combine these two things on one number line. So here's 0. And I'm going to say be greater than or equal to. So go this way. And then here's 2. And I just don't want to be 2. So I could be anything else. Well, when you have multiple restrictions, what you want to do is use the interval that satisfies both pieces. So when I say satisfies both pieces, it's kind of where what I've graphed, the blue and the red, come together. So they start coming together. Where do they start coming together? Over here, I only see red. I have to see blue and red. So that happens first at the 0. Since they both can be 0, I'm going to use a bracket. Then I go, so both are happening, both are okay. But at 2, the red one says don't be 2. So we're going to say skip over 2. But then everything after 2, both blue and red are showing is okay. So 2 to infinity. And that's it for today.